My name is Olivier Jeunen, and I will be presenting our work, A Probabilistic Framework to Learn Auction Mechanisms via Gradient Descent. This is joint work with my colleagues Lampros, Amin, and Ben when I was at Amazon. Let's dive into the problem setting. As I'm sure many of you are aware, opportunities to show ads on the web are typically sold off in real-time auctions. And so the auctioneers that typically design these auctions have many goals. First, they'll want to maximize welfare for the auction participants, which maximizes the value that is being generated by the auction. Now, at the same time, we'll want the auction to be incentive compatible, so it allows for truthful bidding. But there may be other goals. We could try to, at the same time, improve revenue for the seller, or maybe mitigate some sort of externalities on third parties. Think of users who are viewing the ads. Now, when we move towards these more complex objectives, existing work in auction theory falls short, as we can no longer optimize these objectives in an exact manner. And so the research question becomes whether we can somehow learn optimal auction mechanisms from data. Now, to give a bit more detail, we'll be looking at single-slot CPX auctions. So this includes CPM, CPC, or CPA. We'll have a certain ad catalog with ads A and valuations V. For a given context X and a certain target outcome C, such as a click, we can then obtain estimates of welfare from showing this ad in this context. As you can see, it's simply the probability of the target outcome multiplied with the valuation that the bidder has set for this outcome. Now, if you look at the auction mechanisms themselves, well, what exactly are they? Well, we posit that an auction mechanism makes two decisions. The first is an ad allocation decision. Which ads do we show? And we model this as a function pi that, given a context and an ad catalog, is going to give us a probability distribution over the ads to be shown. Then we additionally have a pricing rule. This pricing rule is going to, given the allocation decision, sort of tell us how much the bidder is going to be charged. And so we can say that an auction mechanism is defined by these two functions. Now we can start talking about objectives for auction mechanisms. For example, the expectation of welfare can be written out as this quantity. It's simply the expected welfare for a given context ad pair over all context and over all ads. Now, as we move towards revenue, for example, we get a very similar equation, but the value that is provided by the bidder is now replaced by the price that they need to pay, and we can go beyond that as well. Now, besides these objectives, we've also mentioned that there are some constraints. And so we will typically want to focus on incentive-compatible auctions. And there's much more detail in the paper about this, but for sort of illustrative purposes, we will adopt a bit squashing example here. So we're going to introduce a certain parameter alpha as an exponent to the estimated outcome probability. And this is going to give us an updated ranking score, if you will, in the function f of alpha. And so this updated ranking score is then simply used to compute the first and the second price ad, and then we apply a simple second price rule. And so this will lead to a well-known incentive-compatible auction mechanism, where we now have a single parameter alpha that we can tune to optimize for welfare or revenue or sort of any other objectives that we might have. Now, we can extend this single parameter situation to actually become a function of covariance, this sort of alpha of x. And we will refer to this new variant as the personalized squashing, or p-squash. And so these covariates x can hold any sort of contextual information about the impression opportunity. And we can easily verify that this mechanism is actually still going to be incentive compatible. Now, the goal becomes sort of, can we actually learn the parameters for the function alpha that is going to maximize our objectives? So, for example, can we learn the function alpha of x that is going to maximize the expectation of a revenue while still remaining within this incentive compatible framework? All right, cool. So now we can actually start talking about sort of optimizing auction mechanisms for these objectives. And so what is shown on the slide here is a very simplified example where we have three different ads with three different valuations and three different outcome probabilities. We're adopting a simple second price squashing auction. The plot on the left-hand side is going to show welfare given varying values of alpha, and the plot on the right shows the expectation of revenue given alpha. Now, in this sort of single parameter case, we can very easily visualize this and do a grid search to find the alpha that maximizes revenue, for example. But this will quickly fail when alpha is higher dimensional. What we can see, though, is that both welfare and revenue are discontinuous and non-differentiable with respect to the parameter alpha. And so using standard gradient descent techniques to optimize alpha will fail here. And the reason for this is actually the sorting operation that goes on behind the scenes to obtain the winning and runner-up ads. Now, luckily for us, work exists that actually approximates this hard sorting operation with a soft sorting operation, which looks like this when we try to visualize it. And so, even though this is going to give us a fully continuous and differentiable function, we can see that the surface is still going to be highly non-convex and non-smooth. And so it's really not easy to optimize for using gradient descent. One way to mitigate this issue, inspired by the recent literature, is to use something called probabilistic smoothing. And so we're going to add Gumbel distributed noise to the raw ranking scores during optimization. And this added level of stochasticity will sometimes allow the optimizer to escape local minima. One more advantage here is that we can actually leverage this technique after optimization as well to get stochastic allocation rules. When you're doing this, you will need a bit more trickery to actually get an incentive-compatible pricing rule. There's more detail in the paper about that. All right, so that's the meat of the paper, but does it actually work? We'll look at 4 competing auction mechanisms. So first, a classical second price mechanism, then a squashing mechanism with a single parameter alpha that we optimize via a grid search, then P squash, where we learn this function alpha of x via gradient descent, and GP squash, where we will also leverage this Gumbel distributed smoothing during optimization. But we're still dealing with fully deterministic auction mechanisms. We run experiments on a proprietary data set, and we show relative improvements of estimated revenue, both on the training and test sets here. And as you can see, both P squash and GP squash lead to significant improvements over the widely used second price methods, and even the well-known squashing mechanism. Now, these are still deterministic auction mechanisms. So what will happen if we actually add stochasticity to the allocation rule? One very common concern would be that we might actually lose welfare or revenue by doing this. But so it turns out that this is actually not a huge concern. So what we're showing on the plot here is the variance of the Gumbel distribution on the x-axis. So higher values of beta will be more stochasticity, lower values of beta will lead to deterministic auction mechanisms. And we can see that there's a sweet spot. So if we take beta to be, for example, 10 to the power minus 8, then the plot on the right-hand side shows that we can actually diversify the allocation decisions for almost 20% of auctions that we're running. The plot on the left shows that we can do this at essentially no decrease in revenue. Right. Okay, so to conclude, the main contributions of our paper. We have proposed a probabilistic framework to learn auction mechanisms, and we can do this via gradient descent by using sorting approximations, which has already been done in recent work. Beyond recent work, we propose to also leverage probabilistic smoothing for improved optimization, and we can further leverage these Gumbel distributed noise to allow for stochastic auctions with more detail in the paper. Finally, we show empirically that our method is able to improve over classical approaches on real-world data. So thank you for listening. I'd be happy to answer any questions. Feel free to reach out, and otherwise enjoy the rest of the workshop. Thank you.